Hi dear students, in this session we will discuss about impulse function and response. You know about impulse function. What do you mean by impulse function? An impulse is a signal of infinite amplitude and zero duration. So for an instant of time its amplitude will be high. That means if we are getting a beat on your face, it is like an impulse, right? Because you will get the pain but you don't identify the second when you got that pain. That is an impulse. So an impulse is a signal of infinite amplitude and zero duration. Impulse function occur in circuit analysis either because of a switching operation or because a circuit is excited by an impulse source. So we are dealing with the switching operations. So when a switching operation takes place, the impulse function occurs. That means suddenly we are closing a switch. It is like an impulse. Or if we are opening a switch, suddenly we are opening a switch. That means sometimes there may be cutting of the current or voltage. So whatever be, it looks like a, or it will be affected as an impulse. Similarly, impulse function occur in circuit. Sometimes the circuit is excited by an impulse source. So for dealing such type of circuits, it is better to use Laplace transform method. That means it is better to convert the circuit in S domain equivalent circuit and we can find the time domain voltage or current value. So Laplace transform is used to predict the impulsive current and voltages created during switching and the response of a circuit to an impulsive source. So if we are dealing with the switching operations, that means impulse function occur during the switching operation. So that means impulse function is created with the switching operations. So we will here deal with the two types of circuits, capacitor circuit and inductor circuit, and we will discuss how an impulsive action or impulsive function occur in the case of capacitor circuit or inductor circuit. First of all, let us see the capacitor circuit. So this is the circuit of two capacitors C1 and C2 which are connected to a resistor, and this C1 and C2 are connected through a switch, and here it is shown that the arrow mark is looking like this. That means at t equal to 0 the switch will close. Okay, before the time t equal to 0 switch was open. That is the meaning. That is before time t equal to 0 switch was open, and at a time t equal to 0 switch is closing. So this switching operation, that is this closing of the switch, produces an impulsive function. So we have to analyze that case by using the equations. Okay, so how this impulse function looks like, or how this will appear in the case of this circuit, that is we are going to deal about. Okay, so here we are making some assumptions that here it is given that two capacitors C1 and C2, and C1 is charged to an initial voltage of V0, that is shown here, and at the time switch is closed, and in the circuit the initial charge on C2 is 0. So we are assuming that the C1 is charged to an initial voltage of V0 and C2 has no charge before the time t equal to 0. So we can draw the S domain equivalent circuit when the switch is closed at t equal to 0. So when t equal to 0 the switch will close, so the circuit will look like a continuous closed loop. So we can write, instead of C1, you know that instead of C1 what will be the S domain equivalent? That is, instead of C1 we can write 1 by SC1, but you know that there is an initial charge V0, so we can represent it by using a voltage source. So 1 by SC1 will be connected in series with a voltage source V0 by S. So that is the S domain equivalent representation for C1. So C1 is replaced by 1 by SC1, and also here there is an initial charge V0, so we have to represent that initial charge as V0 by S, and that is represented by a voltage source. So this is the equivalent S domain representation for this C1. Similarly, there is another capacitor C2, but you know that there is no initial charge across C2. That is our assumption. So the C2 will be replaced by 1 by SC2 alone. There is no initial voltage source like this. So 1 by SC2 is the S domain representation for C2. You know that in the case of resistor, the resistor will be replaced by the resistor itself. So R is the S domain representation for this resistor R. And here the switch is replaced by a short circuit, right? Here we are drawing the S domain equivalent circuit when switch is closed. That is why the switch is replaced by a short circuit like this, okay? Or let I be. Here I means I of S. That is I of S is the, or I is the S domain equivalent for the I of t. So you can find out the current through this circuit. Here I is the current. How can you find out this current? You know that current will be equal to total, by Ohm's law, current is equal to total voltage by total impedance or resistance. Here it consists of capacitor, so we have to consider it as an impedance. So total voltage, what is the total voltage? Here only one voltage source, V0 by S. So total voltage is V0 by S divided by total resistance is, here 1 by SC1 is one impedance and R is resistance, 1 by SC2 is other impedance. So we can simply represent as R plus 1 by SC1 plus 1 by SC2. That is the total impedance or total resistance. So we can write this by rearranging R plus 1 by S can be taken outside into 1 by C1 plus 1 by C2. And you know that this is a series circuit. In the case of series circuit, capacitor equivalent capacitance is 1 by C1 plus 1 by C equivalent will be 1 by C1 plus 1 by C2. So we can write V0 by S divided by R plus 1 by S into 1 by C. Okay, this is 1 by C. Instead of 1 by C1 plus 1 by C2, we are writing 1 by C. So 1 by S, if we are taking outside from the term, we will get 1 by S into RS plus 1 by C. So finally we will get V0 divided by, here if you are taking 1 by S and 1 by S cancelled out, so V0 divided by, if you are taking R outside, we will get V0 by R whole divided by S plus 1 by RCE. If we are representing RCE as a time constant of this circuit, then you can find out the solution for this equation. See here, this is the, see here I is the I of S value. I of S is equal to V0 by R divided by S plus 1 by RCE. So to find out the time domain value of the current I of t, you have to take the inverse Laplace transform of this I of S. So L inverse of I of S. Here you can find that V0 by R is a constant value, and here it is in the form of 1 by S plus A form. You may be familiar with that form. What is inverse Laplace transform of 1 by S plus A? 1 by S plus A is, inverse Laplace transform is e raised to minus AT, right? So you can apply that relation here. So V0 by R is constant into e raised to minus T by, instead of A, here is 1 by RCE. So e raised to minus T into 1 by RCE. Here RC is a time constant, so we can represent it as I is equal to V0 by R into e raised to minus T by tau. Tau is RCE. So you can analyze this equation. Here you can see that R is in the denominator side. What will happen to current when the resistor decreases? When the resistance value decreases, current will increase, right? By the relation, I is inversely proportional to resistance. So current will increases when the resistance decreases. That means when the resistance decreases, the initial current V0 by R increases. Why we are calling it as an initial current? Because V0 is the initial voltage. So we can see this V0 by R is the initial component of current. So when I is equal to, when R decreases, initial current increases. What will happen to time constant when R decreases? You know that time constant is RCE. So when R decreases, time constant also decreases, because R and time constant are directly proportional relationship. So when R decreases, time constant decreases. If we are continuously decreasing this R value, what will happen to the current? Current will increase, okay, right? So for a particular value of R, suppose we have two different values of resistance, R1 and R2. Here we are having the relation R2 is less than R1. So whenever R2 is less, corresponding current I2 will be higher. Similarly, when R1 is higher, the corresponding current I1 will be low. I1 will be lower, right? So the current corresponding to R2 will be in the higher position. Similarly, current corresponding to R1 will be in the lower position. So if we are trying to draw a graph between current and time. Here we have the relation for current I with respect to time. So when we are plotting current and time, and if you are giving different values of R, you can see that the curve will start from V0 by R point. But when R2 is lesser value, then this V0 by R2 will be a higher value. Okay, so the curve starts from a higher position, that is V0 by R2 will be in upper comparing to V0 by R1. And you know that what is the nature of this curve? See, this is exponential curve and this is negative exponential, so it will represent a exponential decay. So when we are plotting I and t, so there is an exponential decay of current with respect to time. But you know that here there are two curves, so the current corresponding to R2 will be higher and it will exponentially decay in a faster manner. Similarly, when we are drawing the current and time curve for the R1, then it will exponentially decay, but it will take longer time than comparing to R2. So if you are continuously decreasing this R2 value, what will happen? See, you can see that this current will go up and up higher position and the decay will be suddenly. So when we are increasing resistance R2 or whatever be the value, if we are continuously decreasing the value of resistance, then current will increase and also the decay will be sudden. Finally, for a particular value of R which is equal to 0, then this current will approach as a form of impulse. That means its value will be infinity. Then you know that when R is equal to 0, the current value will be equal to 1 by 0 equal to infinity. Current value will be infinity and it will decay in a fast manner. So it will assume the form of an impulse function. That means that current will be looking like an impulse function starting from the point, this point, and it will increase like this. Okay. So that is our assumption when resistance is 0 in the case of a capacitor circuit which is connected through a switch. When the resistance is 0, the current will be looking like an impulse function. That is the point. So suppose if we have this resistance value R1 and R2, that means there is some finite values for the resistance. And you can see that this is the curve and the area under this curve represents what is the value of the area under this curve. You know, from the mathematical relation, the area under this curve will represents the charge. You know that this is the I versus t curve. So what is the area? Area means current will be multiplied by time. Okay, x-axis will be multiplied by time. So the area under this curve will represent what is current into time. Current into time will be charge, right? You know that current is equal to q by t. Rate of change of charge is current. So when you are multiplying current by time, it will give charge. So the area under this curve represents the charge. So you can write, see, this is not in the form of a particular shape. So for finding out the area, you can use the integral, and integral varies from -0 to infinity value. So you can see the integral 0 minus to infinity, area under the curve is, what is area? X-axis area is I into t, right? So what is the value of I? Y is V0 by R into e raised to minus t by RCE, and time is dt. So for finding out the total area, you have to use integration, that is integral 0 minus to infinity V0 by R into e raised to minus t by RCE into dt. So that quantity will give the charge. So we can represent it as area will be equal to charge Q. So Q will be equal to V0 by R is a constant value, and what is the integration of e raised to minus t by RCE? You know that e raised to minus ax equal to e raised to minus ax divided by minus a. Similarly, you will get V0 by R into minus RCE into e raised to this value, and you have to apply the limit 0, minus and infinity. So once you are applying the limit, you can find that this quantity will be equal to V0 into CE. E raised to minus infinity is 0 and e raised to 0 minus is minus 1. So e raised to minus 0 is equal to 1, and here there is a minus sign. So these minus signs will become plus 1. So we will get the charge or area will be Q equal to V0 into CE. That is Q is equal to V0 into CE. That means here you can find that this area under the curve gives the charge. That means V0 into C is the charge. So when the switch is closed, you can see when the switch is closed, here initially there was a charge. Initially C1 has got a initial voltage V0. So when the switch is closed, then the charge on C2 will be transferred, or voltage across the C1 will be charged to transferred to C2. That means you know that here across C1 there is a voltage V0. Actually C1 has got an ability to store the charge, right? Capacitor has the ability to store energy in the form of charge. So when the switch is closed, it has initially some charge, and due to that charge there is some initial voltage V0. So once the switch is closed and the resistance is lesser value, then there will be some charge from, there will be some flow of charge from C1 to C2, and that charge is Q equal to V0 into C. That is, when this time t equal to 0, switch is closed, so the total charge transferred to C2 will be V0 into C. So thus as R approaches 0, the current approaches an impulse strength V0 into C, that we have already said. So current will have got the form, you know that current is known as a product of charge, rate of change of charge, right? So we can find that current approaches a impulse strength V0 into C. So we can write current will be equal to V0 into C into delta of t. So current has got the form, when R approaches 0, current has got the form V0 into C into del of t. So when R is equal to 0, the finite amount of charge is transferred to C2 instantaneously. And when the switch is closed, the voltage across C2, we can find out the voltage across the C2 as V2 will be equal to V0 into C1 by C1 plus C2. See, this is the, you can see this is the circuit, that is C1 is connected to C2. That means when C2 charge on C2 will be equal to CE into V0 into CE. So you can write the current will be, current can, when R is equal to 0, when that means when this resistance is equal to 0, the current will be in the form of an impulse function. So that current equation will be V0 into CE into del of t, that impulse function. Okay. So at that time the voltage across the C2 will be equal to V0 into C1 divided by C1 plus C2. See, by using this circuit, voltage across the C2 will be equal to, since it is a capacitor, we can use the relation that will be equal to C2 will be equal to V0 into C1 divided by C1 plus C2. Since it is a capacitive circuit, we can write the equation by using the voltage divider rule as voltage across C2 will be equal to V0 into C1 divided by C1 plus C2. Similarly, we can find out the value of the current. Now we have the equation of current is V0 into C into del of t. So this is this equation we have made from the following lengthy steps. But when you are utilizing the Laplace transformed circuit or S-domain circuit, you can directly find out the current equation. See, this is the circuit, S-domain equivalent circuit for the above case. That is, this is a, you have gone through this circuit, and what is the value of the current? Current will be equal to total voltage divided by total impedance. So see, this is the circuit. So when R equal to 0, from the above circuit, when R is equal to 0, then total current will be equal to total voltage divided by total impedance, that is equal to V0 by S divided by 1 by SC1 plus 1 by SC2. Here you can find take 1 by S outside, so that you will get I will be equal to V0 into C1 C2 by C1 plus C2. What is C1 C2 by C1 plus C2? That is equivalent capacitance. So that will be equal to V0 into C. So you can write the equation I is equal to V0 into C. That is, this is the Laplace transformed value of the current. So to find out the time domain value of the current, you can find L inverse of I, that will be equal to V0 into C into what is the inverse Laplace transform of 1? Inverse Laplace transform of 1 is del of t. So current will be having the equation V0 into C into del of t. So here by the switching operation, that is by closing the switch, there should be occur an impulse action, that is closing of switch produces an impulse function, and that impulse function is the current I is equal to V0 into CE into del of t. So the current will depends upon this impulse function del of t. So that impulse function is created by switching action, that is by closing of the switch an impulse function is created. That is the concept behind this circuit. Okay.